your iron monolayer is magnetic or not?
At least locally there should be some field, but the breaking, I think breaking has two contributions. One is from disorder, because strong disorder will also break the Kramer's point. There is no protection from strong disorder. Strong?
No amount of invariant.
But then the strong disorder will change the system Hamiltonian locally.
No,
that's what I mean on the bulk. I mean, it's putting additional atoms, it will deform the surface and introduce a potential. So I think experimental point of view, strong disorder will break the Kramer's point. Actually, to test this idea, now my students are doing. They are now depositing, instead of iron, they're depositing non-magnetic atoms. They're depositing gold. And see what is the contribution of strong disorder and what is contribution of magnetism.
Is this data is also spin dissolved?
We haven't done that yet, but my students also have done the band calculation, but in the calculation it comes out. Yeah. It's very difficult for us to, yeah.
Have you tried other magnetics?
No, this is too early. I mean, this is very recent development. Okay, so then we looked at another compound, this antimony telluride, and it does not have this nice Dirac structure. It has multiple very complex surface structure. And this is the image. This ghost is actually a domain. It's not a real thing. And it's very difficult to get rid of the domain in this compound. Okay, so as I suggested, however, even that compound can be doped, electron and hole doped. One can see that when I electron dope, the electron Fermi surface increases and the hole Fermi surface decreases.
Just doping the surface, right?
Yes, doping the surface, keeping the bulk insulating. When I hole dope the system, then hole Fermi surfaces increase. So it's not gating, but I have some control of the surface.
So this is
I mixed up. This is bismuth antimony.
But this is back to bismuth antimony again.
Yeah. Yeah. So far, materials condition-wise, bismuth antimony alloy is the best topological insulator we have, and I reached my conclusion. So I showed a series of materials that has non-trivial Z2 number by direct imaging of the states and measuring the Berry phase on the surface, and some have this partner switching behavior, others have single surface state. And future directions include what Shu Chang has suggested us to do, what this deposit, try to look for this charge monopole duality. And actually, it was also independently suggested by Frank Wilczek. This is probably more difficult, this look at superconducting proximity effect, but we need a different technique to do that, not ARPES. We can look at the interface electronic structure by doing resonant X-ray scattering. That goes back to my PhD thesis, so I'll have a chance to revisit what I was doing before. And it involved a lot of new instrumentation development. Thank you.
questions.
So with the new instruments, do you hope to be able to get close to 100% selectivity between the two spins?
We actually need an array of Mott detector if I can ever get this funding. We need an array of Mott detector to do a vector spin imaging. Yes, I'll figure out everything on the spin of topological insulator if I have an array of Mott detector, multi-channel, yeah.
Getting back to bismuth, is bismuth expected to be topologically trivial or not?
So far, band structure says trivial, but I have some confidential results that bismuth may be topological.
That is your art
Let's
as
turn off the microphone.
No.
Microphone.
So this is the reason is different. The reason is
I don't know. Only the confidential part.
the reason is the reason is, I can go back and show you why it doesn't break any. It's not a strong departure from Llewellyn or Kane theory. It's a very minor fix, which could be understood intuitively. Let me go there, and that's why I did not write anything there. This is because it can happen that, say, here it's like, this is the antimony side, and antimony would be, it's below the Fermi level. It's semi-metal, right? But it can happen that the bands come close, but they don't invert. So that non-trivial parity is maintained all the way to the bismuth side. So earlier experiment like Dresselhaus and others worked on it. They did not have the resolution to see whether, if your band come close to 1 millivolt, you may not see that. So that's the thing. But to me, what is more important is that getting this pi Berry phase on the surface is it's highly restrictive. It involves so many factors to be true. So that we haven't done on bismuth yet.
The pi Berry phase is going to be there no matter what if you're looking at the Fermi surface around gamma. The question of whether the bands invert, that's a question of what's happening at
No, that we also have to rule out that the resonant states do not contribute to the spin rotation, even in bismuth Fermi surface.
But all the action is going on at the M point. Right. So I think that there's no reason to expect that anything's going to be different about pure bismuth antimony if you're looking around the gamma point.
Yeah, so you always see this like a rough bud on surface phase.
Okay.
Antimony and bismuth.
Yeah.
So the key question is to experimentally to see some qualitative difference compared to pure bismuth and pure antimony at endpoint.
At M point, M point, it's the difficulty is that M point is degenerate with the surface. We cannot separate those things very well. That's what I showed. That is what I was trying to get to. That if they're degenerate with bulk, we don't have much control. What can we do? They're mixed. My trick doesn't work.
No, but you can see which one of the two it touches, right?
This requires very fine tuning where this inversion takes place. That it's like in the X phase diagram, it happens that there's a critical concentration. And how do I know that I suppose it's at 4%, that's where it is currently believed. 4 or 7%? 4%. And it's extremely difficult to fine-tune the bulk material to that composition. Even more difficult for us because when we cleave, we are not necessarily at 4%. So this is extremely challenging from an experimental point of view. That how do I get that fine-tuned Dirac point in bismuth antimony? We of course tried that, but we always either on this side or that side, and then it's mixed with bulk and surface, and we're lost.
Can you do the experiment antimony selenide?
Antimony selenide, it does not have surface states.
Okay.
Huh? This series, as I showed, that we're just beginning to do these things. It takes enormous. It took us 2 years to do bismuth antimony. So antimony selenide, so far, we know that it doesn't have it. It is probably trivial, but I would not bet on it at this point. That's why I did not show the data. But we know that this antimony, this one has 5 surface states, that we know. But if we do the same band calculation, the slab calculation, it will give us 1.
So do you know these 5 are all surface states or
They're all surface state. They're not degenerate with the bulk. That's why we're confident it's 5 surface state. But if you do this same calculation, you'll get 1. Why are we getting 5 there?
Wait, what's going into the calculation?
Oh, just the slab calculation. Shu Chang.
Not doing any. So there's no guarantee that a slab calculation. That
Yeah, of course.
The surface
Of course. Right.
Get anything other than the number of bands mod 2, right?
Yeah, exactly. So that's why I did not compare anything with any calculation. I just did the experiments independent of theory.
So can you, or maybe Fang later on, tell us a bit more about transport?
Transport, I don't do transport measurements.
I haven't settled on the talk yet, but the transport results are not, ready for prime time. So, but I was going to talk on the graphene.
So how is this thing really a bulk insulator?
Okay, all right. So,
like trivial questions like that.
it's an interesting question. So it's been known since the 60s. The resistivity, let's say at 10%, right smack where Zahid was doing the experiment, is insulating light, but then it always saturates at 4 Kelvin.
Yeah.
And the traditional belief was that this was impurity bands.
Right.
But in conversation with Charlie about 2 years ago, we started to suspect that it's actually surface states conducting. So what we've done is to reduce the cross-section systematically.
Yeah.
And you find a very interesting result. As the cross-section is reduced, this insulating trend gets weaker and weaker.
Cross-section?
Sample size. Should I?
Yeah, with this discussion.
So this is not even